So this week, we are discussing the next step from last week's topic, the probability. This week, we're talking about probability distributions. Come on now. The probability distribution, it lists all responses in the or all events in the sample space and their probability. So we have a random variable, and this is just a numerical, for this unit at least, it's numerical, a random variable whose value depends on the outcome of a chance experiment. So then, of course, we have a discrete random variables, which are just a set of isolated points along the number line. Examples of this: rolling a die would create a discrete random variable. Our sample space, 1, 2, 3, 4, 5, or 6. Those are the possible values. Those are discrete values. They're just spaced along the number line. Continuous random variable is, of course, a set of values that include an entire interval on the number line. So not only values along that interval, but every value in between them is part of that variable, the possible values of that variable. Now I'm going to talk a little bit about continuous random variables first, and then I'll come back to our discrete random variables. An example of a continuous random variable would be airplane arrival times. Let's say they are uniformly distributed from 5 minutes early to 20 minutes late. So uniformly distributed means the probabilities are the same along the whole interval, the whole time interval. Continuous means not only just certain values, but every possible value in between, which means there's an infinite number of possible values. Because of that, probability that the variable, the random variable x, equals an individual value has to be 0. Because if the probability of being equal to an individual value is anything other than 0, the fact that there's an infinite number of those values means that the probability would be infinitely large. And we know that our probability of 1 is definite, so we can never have a probability larger than 1. And when we're dealing with these distributions, we have 2 rules that we have to follow. One is, of course, these are probability distributions. So they have to be probabilities. And one of our rules for probabilities is that their value has to be between 0 and 1. Next, for this to be a valid probability distribution, the sum of all of the probabilities, in other words, the sum of the P of X's, has to add up to exactly 1. That's the 100% or definite probability. It's definite that one of those values will occur. So that means that for this continuous random variable, we cannot have any probability assigned to an individual value. In other words, we can't find the probability of individual values. we can only find the probability of x being between two values. Now you might ask, well, is that a is less than or equal to x, or is it just a is less than x? Well, since the probability that x equals an individual value is 0, those are the same. There's no difference between a is less than x and a is less than or equal to x, or x is less than b, or x is less than or equal to b. There's no difference because the probability of being equal to an individual value is 0. Now remember, this is only for a continuous random variable. This is true. So let's look at this distribution here. The main way we approach a continuous random variable is using an area model. So for this, what we defined here, that this arrival times being between uniformly distributed from 5 minutes early to 25 minutes late, we're going to go ahead and set up a number line here. And I'm going to put uniform, means it's all the same all the way across. So it's just going to be a rectangle like this. Now we said the sum of this probability has to be equal to 1. So that means the area of this rectangle has to equal 1. So the length here from -5 to 20 is 25 units. So this height here has to be 1 divided by 25, or 0.04. So since we know that that's 0.04 tall, we can use that to find probabilities. Find the probability that we are between 5 and 15 minutes late. So that x is between 5 and 15. Well, 5 to 15 is here. That's a width of 15 minus 5. And we're going to multiply it by that height of 0.04. That'll give us the area of that section. And that comes out to be 0.4 is that area. So that's our probability. Probability of being between 5 and 15 is 0.4. So for right now, all of our continuous probability models are going to be, either rectangles or triangles or whatever, and we need to find those areas between those two values. We'll go over next week. We'll look at continuous random variables, continuous probability distributions a lot more closely in the normal distribution, which is the main continuous probability distribution. This week, we are focusing on those discrete distributions. So a discrete distribution can be listed out. We can list the value and the probability of that value. So if we look at rolling a die as our example here, our possible values, well, we could roll a 1. That would be a probability of 1 out of 6. A 2 would have a probability of 2 out of 6. Or sorry, 1 out of 6. A 3 is a probability of 1 out of 6. Rolling a 4 has a probability of 1 out of 6. And of course, all these values up through 6 have a probability of 1 out of 6. They're equally likely, so they all have the same probability. It's just 1 divided by the number of possible results. That's kind of a boring probability distribution. So let's do another function. We're going to let x equal the number of heads from flipping 3 coins. So let's take a look at this. Let's draw out our possibilities here. We could have first coin could be heads or tails. Second coin can be heads or tails. Third coin. Could be heads or tails. So if we draw our connections in here, the first flip, we can get heads or tails. If the first one's heads, the second coin can be heads or tails. If the first two are heads, the third one can be heads or tails. And we draw our branches on our tree diagram to branch that off for each one of them. And our possible outcomes are then found by following these branches. So like I might trace this up here, heads, heads, and heads. So this outcome was heads, heads, heads. This was heads, heads, tails, if I follow the branches. This one's heads, tails, heads. Heads, tails, tails. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads. And tails, tails, tails. So we count there are 8 different possible results we can have there. Let X, remember, is the number of heads. We could have 0 heads. There's only one that has 0 heads. That is all 3 tails. That's 1 out of 8, or 0.125. We could get 1 head. Well, there are 3 in there that have 1 head out of the 8. So that's 0.375. We could have 2 heads. Once again, there's 3 out of 8 that have 2 heads. So 0.375. Or we could have all 3 of them heads, and there's only 1 out of those 8 outcomes that has all 3 of them heads. That's 0.125. So if we look at this, first, we see all of these are between 0 and 1. That meets our first requirement of our distribution. And if I add all these up, it adds up to exactly 1. That meets our second qualification to be a distribution. So that is a valid probability distribution. So I might ask, what is the probability of 1 or less heads? Well, highlighter here. 1 or less means 1 or 0. So that really means probability of 1 plus probability of 0, which is 0.125 plus 0.375, which equals 0.5. So that's that probability. Let's take a look at a little bit different distribution, a little bit more complex probability distribution here. So let's look, we did an example a couple of weeks ago with the number of classes students are currently taking. So let's say we've randomly selected students and we've surveyed them and we've come up with these probabilities. The probability of a student having only 1 class is 0.10. Probability that randomly selected student is taking 2 classes is 0.25. Probability they're taking 3 classes is 0.35. Probability that student is taking only 4 classes is 0.15. And the probability that student is taking 5 classes is also 0.15. All those probabilities are between 0 and 1, so that's valid there. And if I add these up, they add up to exactly 1.00. So that is a valid probability distribution. Now we could ask questions like, what is the probability X is less than or equal to 3? That's probability of 1 plus probability of 2 plus probability of 3, less than or equal to 3. So we can just add those up, which adds up to 0.70. Now that's very different, not very different, but it is somewhat different from what's probably X is less than 3, that a randomly selected student has less than 3 classes. Well, that no longer includes the 3. It includes 1 and 2. So that's 0.10 plus 0.25, or 0.35 is that probability. You'll notice here the difference between those is just the probability of 3, because that's the one that's missing from the less than or equal to 3 to the strictly less than 3. The 3 is removed. So the difference between those two resulting probabilities is that probability of being 3. Now, one thing that we looked at last week with our probabilities that some people struggled with is complements. What's the probability that x is less than or equal to 4? Well, I could add up probability of 1 plus probability of 2 plus probability of 3 plus probability of 4. I could do that. Or I could see that that includes everything in my sample space except the 5. So I could just do 1, which is the probability of the whole sample space, minus the probability of 5. So 1 minus 0.15 is 0.85. That's a little quicker than having to add up all 4 of those other probabilities. Likewise, probability that x is at least 1, or actually in this case, let's say greater than 1, because there is no 0 in this case. The probability that x is greater than 1, well, that's everything but the 1. That's the 2, 3, 4, 5. So probability of 2 plus probability of 3 plus probability of 4 plus probability of 5. Or I could do just 1 minus the probability of 1, which is simply 1 minus 0.10 or 0.90. So you can save yourselves a lot of work by being able to use those complements. Next, let's talk about finding the mean of a probability distribution. It is called the expected value. And the notation is E of x, expected value of x. Step 1 is you're going to multiply x times p of x. So let's go up here and do that. Let's add that column. So 1 times 0.1 is 0.1, 2 times 0.25 is 0.50, 3 times 0.35 is 1.05, 4 times 0.15 is 0.60, and 5 times 0.15 is 0.75. So I multiplied those all together. Step 2 is take the sum of those. Add those all up. The sum is 0.30 or 3.00. That is my expected value. Expected value is 3.00. What that is saying is, if I randomly select students and ask how many classes they're currently taking, or use the registration to see how many classes they're currently taking, if I select a bunch of students and record the number of classes, and then I find the mean of those, I expect the mean number of classes to be 3. So on average, students will be taking 3 classes. While we discuss mean, we should probably discuss standard deviation. And of course, variance will be a part of this, or this discussion as well. First step, find the mean. We already did that. E of x equals 3. Step 2, just like with individual values, is subtract the mean from each value. So we're going to say x minus E of x for each. So up here, x minus E of x. Well, 1 minus 3, remember 3 is our expected value we calculated. 1 minus 3 is negative 2. 2 minus 3 is negative 1. 3 minus 3 is 0. 4 minus 3 is 1. And 5 minus 3 is 2. So we've done that. We subtracted. Next, we're going to take that x minus E of x and we're going to square those values. So negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, and 1 squared is 1, 2 squared is 4. So we've squared each of those values. Now, if we were doing just individual values here, oops, did somebody have a question? Okay. Sorry, I thought I heard somebody speaking up. If we were just doing individual values here, this is the point where we would add these. These are not individual values, they're part of a distribution. So we have to do a step in between before we add, and that is to do the P of X times the X minus E of X. The P of X is kind of like or X minus E of X squared. That's kind of like their frequency in the frequency table. So 0.1 times 4 is 0.4. 0.25 times 1 is 0.25. 0.35 times 0 is just 0. 0.15 times 1 is 0.15. And 0.15 times 4 is 0.60. Step 5 now is going to be to find the sum. The sum of these, if I add them up, it looks like it's 1.40. That is the variance. If I want to find the standard deviation, I need one more step. It's the square root. Square root of 1.40 equals 1.18. I believe that is the standard deviation. So we can find the mean and standard deviation of a probability distribution fairly simply just by doing those steps. It's a lot of work. You can use Excel to organize it if you want to. Obviously, I created this distribution to make the numbers work fairly easily, so I didn't have any really ugly calculations there. So I see a comment here. For most of the distributions, there's a shortcut for finding variance and standard deviation. But for a discrete distribution, for a regular discrete distribution that is not a special distribution, that is the only way to go, is you have to go through that process. Okay, so let's take a look at some of our special distributions. Oops, somebody did a comment there. Let me go back. Oh, that's it. Okay. So the first special distribution I want to talk about is called a binomial probability distribution. Now, the binomial probability distribution has some important requirements. First, what a binomial probability distribution is technically we're completing a simple experiment and we're doing it over and over again. Each time we do that experiment, it is called a trial. In a binomial distribution or binomial experiment, there's a fixed number of those trials. We're repeating that simple experiment a fixed number of times. We determine before we start how many times we're going to do it. That number that we're going to repeat it is n. Second requirement is each trial, each little experiment, simple experiment, has two possible outcomes: a success or a failure. Now, that doesn't mean that there's only two possible results. I mean, two possible outcomes, you always go to flipping a coin because there's heads or tails. That's only two possible results, period. But you can have more than two possible results and still be binomial. For example, flipping a coin. Or not flipping a coin, or rolling a die. You define a 1 or 2 equals success, And, oops, gotta get my window expanded here. And then you could define 3, 4, 5, or 6 equal failure. So even though there's more than 2 possible results, we've split them into 2 categories, 2 cases, so that there really are only 2 outcomes. Second, we have independent trials. So it doesn't matter if I've rolled a 1 4 times in a row. The probability of rolling a 1 on the next trial is still 1/6. The result of one trial does not affect the probability on the next trial or any of the trials after that. The trials have no effect on each other. Because of that, then, probability of success is a constant. And we refer to that as P, is that probability of success on each individual trial. So X equals the number of successes out of those n trials. So let's say we're going to roll this die 5 times. Our distribution here, our possible values, we could have 0 successes. We could never get a 1 or a 2 on that die in those 5 trials. We get everything, all the 5 rolls could be 3 through 6s. We could have 1, 2, 3, 4, up to 5 successes on that die. Now those probabilities, however, are a little bit trickier to calculate. For a binomial distribution, the probability that X equals an individual value for n trials and P probability of success is equal to n choose A times the probability of success to the power of A times 1 minus our P, 1 minus our probability of success, to the power of n minus A. Now let's talk about what that NCA means. NCA is n items, I say from n items, choose A of those items. In other words, it's out of 5 rolls of the die, how many different ways can I get 2 successes? I could have the first 2 could be successful. The last 2 could be successful. The first and the last could be successful. The first and the third could be successes and the rest failures. We need to figure out how many different ways that can happen. And that is what that n choose A is. N choose A is calculated using a factorial. It is n factorial divided by A factorial times n minus A factorial. So first of all, what does factorial mean? Well, factorial, let's put in the numbers here. Let's do 5 choose 2. Let's say we're going to do 2 successes. So that would be 5 factorial divided by 2 factorial times 5 minus 2 factorial. In other words, 3 factorial. So that would equal 5 factorial is 5 times 4 times 3 times 2 times 1. That factorial means times that number times all the whole number smaller than it all the way down to 1. So 2 factorial is 2 times 1. And 5 minus 2 is 3 factorial. So it's 3 times 2 times 1. And what generally happens in these combinations here, the 5 choose 2 is called a combination, is what you see here. The 3, 2, and 1 and the 3, 2, and 1, they divide out. So then what I have is on top 5 times 4 is 20. On bottom 2 times 1 is 2. 20 times 2 are 10. That is saying there are 10 different ways to choose 2 successes out of 5 trials. So what is that probability that x equals 2? Now, first of all, I'm going to do a shortcut notation. I'm just going to probability of 2 means probability that x equals 2. That's going to be 5, choose 2, because we're out of 5 trials, we want 2 successes, times our probability of success is 1/3 to the power of, we're going to have 2 successes, times our probability of failure is 1 minus 2/3, that's our 1 minus p, to the power of the number of failures. Well, that's going to be n minus a, or 5 minus 2. If 2 out of the 5 are successes, 3 are failures. So we know that 5 choose 2 is 10. And of course, this is 1/3 to the power of 2 times 2/3 to the power of 3. Let's calculate that quick. So 10 times 1/3 to the power of 2. Now I have to make sure I arrow out of that power before I continue. Times 2/3 to the power of 3. And I get 0.3292 is my probability there. Now I could fill that into my distribution over here as my probability of 2. And I can find those probabilities individually, but there's a shorter way of doing it. Our TI-84 calculator has a built-in binomial function. Actually, it has 2 built-in binomial functions. It has binomial or binom PDF. PDF stands for probability distribution function. This gives you the probability of individual values. Probability that x equals a. Then there's binom CDF. This stands for cumulative distribution function. This gives probability that x is less than or equal to a, the value we put into it. So here, if we wanted each of these individual values, we would do the binom PDF. If we wanted cumulative values, less than values, we would do the CDF. Let's do some examples here. I'm going to go over to the next page. So we still have a binomial experiment with n equals 5 trials, and p, the probability of success, equals 1/3. Find, let's do the probability of getting 3 successes out of those 5 trials. So this is just a single value, x equals exactly 3. I'm going to put this out in words, of exactly 3 successes. That's probability that x equals 3. And that's going to be using a binom PDF because it's exactly equal to 1 value, to 3. So let's go to the calculator here. To get to our distributions, you see DISTR, that's our distribution menu. It's a second function above the variables menu. So I do second distribution. It brings us to our list of probability distributions. We've got normal distribution here, some commands for that we'll look at next week. T distribution is another one of those continuous distributions we'll look at next week. Chi-squared is coming up in a few weeks. You have to arrow down a ways to find binomial. There it is. We've got binom PDF and CDF. We just want PDF here because we're looking for the probability of being equal to a single value. It's not, notice it says binom PDF on top, so we can reaffirm that we got the correct function there. Our number of trials, well, n equals 5 trials. P, our probability of success on an individual trial, is 1/3. So I can do 1 divided by 3 for that value. Our x value, we wanted exactly 3 successes. Then we select paste, and it's going to put it in our function. The function, the binomial PDF function is xpn. Some of you might have shut off that stat wizard and you just have to do the 5, 1/3, 3. It's actually quicker to do it that way, but we have our calculator set up with the stat wizard just to make it easier to enter the information. We get 0.1646 is that probability. So there it is, 0.1646. Well, it doesn't stay that simple. The probability of being equal, exactly a value or equal to a single value is simple to find. It's just that binomial PDF. But let's say that I want to know what is the probability of having 3 or less successes. That's probably that x is less than or equal to 3 or less. That means we're going to be doing a binomial CDF. CDF, cumulative distribution function, means less than or equal to. In other words, we start at 0 and we add up all the probabilities up to the value that we're looking at. So on the calculator, go to second distribution. We go down to binomial CDF. Now I'm going to show you a little bit of a shortcut rather than having to arrow down the whole time. Binomial CDF is option B. So let me clear this out. I'm going to go in again. Second distribution. And I can just do alpha B. And that'll give me the binomial CDF. So I don't have to arrow down, do 10 arrow downs to get to it. So our number of trials is 5 still. P, or probability of success, is 1/3. So 1 divided by 3. Oops. 1 divided by 3. And we wanted 3 or less successes. So we put in 3 there because it's CDF, cumulative distribution function. When we put in 3 there, we're saying we want the probability of being less than or equal to 3. We get 0.9547 is that probability. Now that looks very similar to this next one, but it's actually going to be quite significantly different. What's the probability of having less than 3 successes? This is probably x is just less than 3, not less than or equal to. Well, this is still a binomial CDF, but we have to convert it into something that's of the form less than or equal to, not just strictly less than. Well, since this is discrete, probability of being less than 3 is equivalent to the probability of being less than or equal to 2. Because there's nothing between 2 and 3 that we're missing out on there. So we're still going to do a binomial CDF, still a cumulative distribution function, but we're doing it for 2, not for 3. Let's go to the calculator. Let's go on. There we go. So second distribution. Now again, I'm just going to do alpha B as the binomial CDF. Still 5 trials, still probability of 1/3, but I'm going to change this from 3 down to 2. Now it's only 0.7901. So you'll notice that the difference between these two probabilities here is the probability of being exactly 3, because that's all that's missing here. This is 0, 1, 2, 3. This is 0, 1, 2. So the difference should be that probability of being equal to 3. So those are our probabilities of being less than. What if I ask you for the probability that we will have a value of more than 3? So this is probability x is greater than 3. Does not include the 3. Well, the complement of that is what we want. Since this is greater than, our calculator only works with less thans. So we're going to do the complement, 1 minus the fact that x is less than or equal to 3. Greater than 3 does not include the 3. So its complement has to include the 3. That's the x is less than or equal to 3. So again, this is a binomial CDF. But when we punch it in the calculator here, before we punch it in, we do 1 minus. And then we do second distribution. Still binomial CDF, so alpha B. 5 trials. Now we're taking out 3 or less. So I'll put the 3 in there again. And I get 0.0453. Now, what if I forgot to put in the 1 minus first? What if I do second distributions, binomial CDF, and I put in all this information and I realize, oh man, I forgot to do the 1 minus. No problem. I just type in 1 minus and then do second answer, telling the calculator to subtract that previous answer from 1. And I get the 0.0453. An accepted standard in probabilities, by the way, is, unless you're told otherwise, 4 decimal places. Now, one of the assignments last week said 3 significant digits. Well, that's because there's a significant difference in the size of those results. 3 significant digits is you take the first non-zero digit and then 2 more after that. So this one would have been rounded off right here after the 4. Same here, first non-zero digit and then 2 more, we would have rounded there. This one, however, the first non-zero digit isn't until there, so we would have gone all the way there to get 3 significant digits. The reason they use 3 significant digits rather than saying 3 or 4 decimal places is because one of the numbers there was like 1.17 e negative 5. What does that mean? Well, it's scientific notation. So you have to move the decimal point way over. And if you'd have rounded to 3 or 4 decimal places, the answer would have been 0. And we didn't want that. We'll take a look at an example of that e negative 5 before we're done here. Finally, what's the probability that is at least 3 successes? So this is probability x is less or greater than or equal to 3. Well, the complement of that was 1 minus probability x is strictly less than 3. The 3 was included in the greater than or equal to, so it can't be included in the less than. Well, we need to have this in terms of less than or equal to. So we convert that less than or equal to 3 to that less than, strictly less than 3 to being less than or equal to 2. So it's 1 minus the probability that x is less than or equal to 2. So again, it's a binomial CDF. We're just adjusting for that probability that it's only 2 this time. So go to my calculator. Second distribution, binomial CDF. Change this to a 2. Now you'll notice I forgot to do the 1 minus. So this is just going to be that number that we're used to. So we're going to do 1 minus second answer, 0.2099. Is that probability? You'll notice, by the way, that that is a complement to that being less than or equal to 2, or 1 minus being less than or equal to 2. Makes sense. Those are complements. Dealing with these binomial probabilities, these last 4 examples here can be tricky. If the probability is less than, well, do I include the number or do I go 1 below it like we had to do here? If it's greater than, is it 1 minus the probability of that number, or is it 1 minus 1 lower than that number like we had to do here? I don't have time to do a lot of examples with that tonight because we have 2 more distributions to go through. But I did put some worksheets in week 4. There's some binomial hints object I put out there that has a document that goes through some things with the binomial distribution that might help you out with that. It goes through it again for you that might help clarify that. But that is a tricky thing, is when is it less than the value given, or when is it less than or equal to 1? We have to go 1 below that value given. That can be a tricky decision to make. With our binomial distribution, the expected value, there's a shortcut. It's just n times p. So here there's 5, n is 5, p is 1/3. That equals 2.667. 6667 will go. Sorry, 1.6667. 1 2/3 basically is that result. So we would expect if we repeated this experiment over and over again. So we did the 5 rolls of the die and counted the number of successes out of those 5 rolls. Then we did it again and again and repeated that several times. On average, we'd get 1 2/3 successes per every 5 rolls. The variance of that is n times p times 1 minus p. So that's going to be 5 times 1/3 times 1 minus 1/3. Which just equals 1.1111. Standard deviation of x is just the square root of the variance. So the square root of that 1.1111. Now, typically, I would just do the square root. I don't stop at the variance. I would be doing the square root of 5 times 1/3 times 1 minus 1/3. And I'd be doing it that way. Giving us, I'm going to do this off screen. I'm going to do the 5 times 1/3 times 1 minus 1/3. I get 1.054. 1 if I round it to 4 decimal places. So finding the mean, variance, and standard deviation of a binomial distribution is pretty simple. We have those shortcuts for it. Well, remember the binomial distribution required p to be constant. In other words, either it is done with replacement, the selection is done with replacement, or we have an infinitely large population. If it's an infinitely large population, then it really doesn't change the numbers whether we put the 1 back or not, because it's still an infinitely large population. Now, realistically, we never have an infinitely large population. We can't have an infinite amount of anything. So what we say is if n is less than 0.05, in other words, 5% of the population size. Capital N is the size of the population. So if the number of trials, number of samples is less than 5% of the population, then we're okay to still use the binomial distribution. If n is greater than 0.05, or 5% of the population, then we use something called a hypergeometric distribution. Hypergeometric distribution is not part of this class. I did an example in my recorded lecture that I posted. If you want to go see it, it's out there. This would be like drawing a hand of cards out of the deck. What's the probability of getting 3 clubs? Or what's the probability of getting 2 aces in that hand? Obviously, you're drawing 5 cards. That's more than 5% of the deck. So we can't use binomial approximation. We would have to use hypergeometric distribution. It's an interesting and useful distribution, but it's not something we're using in this course. So I'm not going to go over it here right now. But that's when it gets used, is when that probability of success is changing because we're not using replacement. Well, very closely related to the binomial distribution is something called the geometric distribution. Now, the one I just mentioned was the hypergeometric. This is just a geometric distribution. There, I finally got it. The geometric distribution measures the number of trials until the first success. So it does not have a fixed number of trials. However, all of the other qualifications of the binomial distribution hold for the geometric distribution. In other words, trials are independent. The results of one trial, if we fail on one trial, doesn't change the probability of being successful on the next. Each trial has two possibilities. Still that success or failure. And of course, P equals the probability of success on each trial. So X now is not the number of successes out of a set number of trials, because there is no set number of trials anymore. X is the number of trials until the first success. Now, for example here, let's say that, now let's do this. The probability that X will equal A is equal to 1 minus P to the power of A minus 1. If we're going to have our first success on the 8th trial, on trial A, all the trials before that had to be failures. So there's A minus 1 failures before that, times P, the probability that last one is a success. So let's look at our example from before, where P is 1/3. So we're rolling a die, a 1 or a 2 is a success, 3, 4, 5, or 3, 4, 5, or 6 are failures. What's the probability that our first success will be on the 4th trial? Well, that's going to be 1 minus 1/3 to the power of 4 minus 1, or 3, times 1/3. So let's do this on the calculator. So 1 minus 1/3. I'm just going to do the power of 3. 4 minus 1 is 3. Make sure you arrow out of that power, times 1/3. We get 0.0988. So 0.0988 is the chances that we would get that first success on the 4th roll, 4th trial. Let's look at an example here for this geometric distribution. Let's say we know that 45% of students carry their laptop in their backpack. So we are going to randomly stop students and ask if they are carrying their laptop. So what is the probability that the first student that is carrying their laptop is the 3rd student? So that means that the first 2 are failures. They don't have their laptop. So it's 1 minus 0.45 is the chance that they don't. If 0.45 is the chance that they have it, 45%. 1 minus 0.45 is the chance that they don't have it. That'll be the power of 3 minus 1, or 2. In other words, 2 of them don't have a laptop. The first 2 don't. And that'll be times then the last one is having a laptop is a probability of 0.45. So I'll calculate that off screen. I know that 1 minus 0.45 is 0.55, so that's the power of 2. Make sure arrow out of that times 0.45. Gives you 0.136125. Now, normally we'd probably round that off to 0.1361, but I left it just because it does terminate pretty quickly there. So there is no less than or equal to really for the hypergeometric. You would have to figure out all, or for the regular geometric distribution, you'd have to figure out all of those values individually and add them up. There isn't a cumulative function that we're going to deal with on the calculator there. The expected value for the geometric distribution is just 1 divided by p. So for this example here, 1 divided by 0.45 is, what is that, 2.222, I believe. Let me double check. It is 2.222. So we would expect on average between the second and third student would be the first ones to have their laptop with them. So that's the geometric distribution. It's relatively simple. Our third and final discrete distribution that we're going to talk about is called the Poisson distribution. Now, this one is not in the textbook. So because of that, I put up, there's I believe it's 4 or 5 video links in week 4 that I put up. It's in a separate folder. I have my video that I made, and then I put links to some YouTube videos into a different Cengage textbook that does the Poisson distribution. Now, because of that, there's not going to be Poisson questions in the WebAssign homework because it's not in our textbook, but there will be some in the application assignment. So watch out for those in the application assignment. So for the Poisson distribution, what it does, we have 2 parameters for it. R is the number of, well, usually Poisson is used to find defects. So the terminology is used as defects in a given interval. That interval could be time, it could be distance, it could be length, any sort of interval. Lambda is the average number of defects in an interval of that length, of that size, I will say. It could be time or distance or length or any type of interval. Now, lambda, I wrote it out as a word, but it's really, it looks like that. It's that Greek kind of upside down Y. So the formula, probability x equals R, is e to the power of negative lambda times lambda to the power of R divided by R factorial. So that factorial comes into play again. We'll stretch this out so it looks better. There you go. So let's say that we have, there's going to be 2 examples we'll do here. Our first example is, let's say on average, every mile of fiber optic cable, this is for communications, telephone, internet, TV, and stuff like that, has 6 nodes. Nodes are taps coming into the fiber optic cable. So this would be what would be going to your home. So this is obviously not the big trunk lines between cities. Those have no nodes on them. It's the cable going through your neighborhoods with the fiber to the home. So it's being tapped off for each home. What is the probability that a 9-mile stretch of fiber optic cable has exactly 50 nodes? So that probability that x equals 50 is E. First of all, we have to find lambda. What would the average amount be? Well, it is 6 nodes per mile times 9 miles. 6 times 9 is 54 nodes. So our average would be 54 nodes. That's lambda. So it'll be e to the power of negative 54 times 54 to the power of 50 divided by 50 factorial. This would be almost, well, it would be impossible to do by hand, but the calculator handles it fairly well. Let's go to the calculator. First of all, the e to the power of, we have this ln key down here. Notice above it, we have an e to the x. That's what we're going to use. So we do second ln gives us e to the power of x. We're putting in negative 54 there. We have to make sure we arrow out and then do times 54 to the power of our R value is 50. We want 50 successes. Again, make sure we arrow out of the power, divide 50. Now we're going to go to the math menu here, PRB, option 4 there is factorial. That's 50 factorial. That gives us 0.0484. So the probability of a 9-mile stretch of fiber optics having exactly 50 nodes is 0.0484. Now, this is kind of a complex formula. It'd be impossible really to do it by hand without a calculator. But with the calculator, it's fairly simple to enter. In fact, it was simpler than doing the binomial probability formula would be on the calculator. So because of that, we can use the Poisson distribution to estimate binomial probabilities, but only if p is extremely small. I mean, the absolute limit is it has to be less than 1%, but it should be even smaller than that. Let me show you an example here. So let's say we know that 0.08% of calculators have a defective display when new. What is the probability that 3 out of a batch of 5,000 have defective displays? We can use the Poisson distribution here. Lambda will be 0.0008. That's the 0.08% as a decimal. We have to move the decimal 2 spots. Times 5,000. That would give us an average of 4 defectives out of 5,000. Let me finish this question and then I'll get to your question in the chat there. I see some of you probably have to leave for other meetings. I understand that. We'll go ahead and we'll see you next week. So we got, now that we have lambda, the probability of x equals 3 is e to the power of negative lambda, negative 4, times 4 to the power of 3 divided by 3 factorial. So let's do that on the calculator and get an answer here. So second e to the x, negative 4, arrow out, times 4 to the power of 3, arrow out of the power again, divided by 3 factorial. Okay, 0.1954. Now remember, that is an approximation of the binomial distribution. This was 5,000 trials, 0.0008 is our probability of success, and we wanted 3 successes. Let's compare the two and see how they compare. Now, why would we use the Poisson distribution instead of binomial? because we have the TI-84 calculator, which has the binomial distribution built in. We would just use the binomial distribution. But a standard scientific calculator does not have the binomial distribution in it. But most scientific calculators, standard scientific calculators, have the e to the power of, and they have the factorial function on. So almost every simple scientific calculator, $12 or $13 scientific calculator, is capable of doing that Poisson distribution fairly quickly. Doing the steps for the binomial distribution is more difficult. The TI-84 has the binomial distribution built in, which makes it easier, but we won't always have that. But let's do the binomial distribution, the binomial probability, just to see how they compare. The second distribution, binom PDF, 5,000 trials. Oops, 5,000, not 50,000. 0.0008 is our probability. And we want 3 successes, or 3 defects, I guess is what we're looking at. 0.1954. Now you'll notice that's the exact same value we had before, but we're rounded to 4 decimal places were exactly the same. If we went to 5 decimal places, it would be slightly different. So it is an approximation. It isn't exactly the same, but it is really close. Okay, so that is our new material. Let's take a look at how Minitab fits into all of this. Now, Minitab is way more helpful in organizing data and doing graphs like we did in the first couple of weeks. We noticed last week that Minitab didn't do a lot with the probabilities. If somebody had a question. Okay, so when you attempt the Poisson equation, if you're getting a syntax error, chances are usually the most common problem is when you enter that e to the, so you do e second ln to get the e to the x, make sure you use the negative key down here, not the minus key, the subtraction key. There's a negative key down here. That's usually the most common syntax error, is using that. Okay, hopefully that answers your question there. If it doesn't, let me know and we'll come back to it again at the end here. So let's go to Minitab. Like I said, Minitab, we saw last week for probabilities. It did help with the contingency tables, but that's about it. It's no faster than the calculator for probabilities. It's great for those graphical displays of organizing data and graphing data from the first couple of weeks. But it can do some of our distributions. Let's look at a binomial situation where the probability of success on an individual trial is 0.35 and n equals 15 trials. So I'm going to move this up so you have a little more room. So I'm going to put my successes in here. I can hear them from 0, 1, 2, 3, 4, 5. I don't think it does. No, it does not. Okay. So 0 through 15 are my possible successes here. I'm going to put here, I'm going to put in probability. I'm going to go to calc, probability distributions, binomial. Now I'm going to just click probability here. My number of trials is 15. That's what we had said before over here. Event probability, that's my probability of success on a single event. That's 0.35. I'm going to do just an input constant here. I'm going to say, what is the probability of getting exactly 4 successes? I click OK. It's going to calculate that probability and put it up here. It does tell me that that was 15 trials and a probability of 0.35 on each trial. Probability of 4 successes is 0.179247. Minitab is automatically set to go 6 significant digits, so 6 decimal places. What if I wanted this whole distribution? Well, this is the one place where Minitab does help out a little bit. It'll show us the whole distribution at once. So instead of input constant, I'm going to click input column. I'll leave my number of trials and my event probability in there. And then I'm going to do my input column is going to be the successes. My output storage will be the probability. I set that up to accept those probabilities in that column. And notice it fills them in. Probability of 4 is the same as what we had before, the 0.179247, but it filled in all the other probabilities in the table for us as well. I could also do cumulative probabilities. I'll go back to that function, calc, probability distributions, binomial. Now I'm just going to click cumulative. Now I'm going to switch this here from being probability column to the cumulative probability column. It fills in the cumulative probabilities there. Now notice it goes up to 1. The last one should always be 1 in a cumulative distribution. Now because it has the 1 in front here, it only goes 5 decimal places instead of 6. And these probabilities are so small that once we hit 5 decimal places, they round off to zeros. So that's why we have a cumulative probability of 1 for all 3 of those. These do have probabilities, but it's just so small it rounds out to 0 when it rounds off. Well, let's look at, so that is our binomial distribution. Let's look at what if we wanted to use this experiment. We're still going to keep the 0.35 as our probability of success. I want to know what's the probability that we have our first success on the first trial or second or third or whatever. This is a geometric distribution. So calculate probability distributions, geometric, right after the binomial. I'm just going to do a regular probability. My event probability is 0.35 again. I could do an input constant, ask what's the probability that it's the 4th trial that gives us the first success. And that gives us that probability right there. Or go back to this menu. I go input column and I'll put in the trials. Now I forgot to name the output range. Oh, I did do first success. Okay, I did name it. Otherwise, I could have just put in C8 if I needed to for that. And we hit OK and it fills this in. Notice very little chance that we're going to keep going past 7 or 8 trials here. It's, less than a 3% that it's going to take 7, less than 2% that it'll take 8. So those probabilities get very small after that. So that is our geometric distribution. Poisson distribution also has a function here. Let's say that on average, we have 4 students that fail a section of a math course at the university. So on average, each section has 4 students who fail. I want to know, okay, so out of a section, we could have 0 failures. Let's say a section has 20 students in it, so we'll go up through 20. Now I'm going to name, I'll just leave this unnamed for now, and I'll show you how it works, how I don't need to name it. So we're going to go calculate probability distributions and Poisson. Just regular probability, not cumulative. Our mean is 4. On average, we'd expect 4 students to fail a section. Our input column is the fails. Our output column, I did not name it, so I'm just going to go C13. And it does do it. I can still name it now afterwards. Is the probability of failing, of that many failing. So you can see between 3 and 4 is the mean here. 1 divided by 0.35 is like 3.142857, something like that. So between 3 and 4 is the mean. Those are the 2 highest probabilities. And there's the probabilities of that many students failing the course. So anyway, those are those 3 distributions in Minitab. Let's get out of here. Last thing we have to do for the night is our meat quiz. This is a little bit longer quiz tonight, so I am going to put it up on the board and get right into it. So we have a statistics course, and we find that on average, 14% of students earn an A in their statistics course. So that is saying that P, probability of success of earning an A, is 0.14. Taking a random sample of 20 students, so that's saying N equals 20. Find the probability that exactly 6 earn an A. So that's P that X equals 6. Well, that's just a binomial PDF. So we'll go to the calculator. Second distribution, binomial PDF. 20 trials. Probability of success of 0.14, because that's the 14%. We want 6 successes. Okay, we did something wrong there. Oh, I had an extra key in there. So let's do that again. Second distribution, binomial PDF. There's our values, are all right. Now it should turn out. There it is, 0.0353. There we go. The next one, at least 5 earn an A. That's probably X is greater than or equal to 5. That's equal to 1 minus probably X is less than 5, which is equal to 1 minus X is less than or equal to 4. So we're going down to 4. Or up to from 1 minus the 0 through 4 because we want at least 5. So we're keeping the 5 through 20. We're subtracting out the 0 through 4. So second distribution. Now it's binomial CDF we want. Still 20 trials. Probability is still 0.14. Now we haven't used these numbers in the binomial CDF, so that's why we have to re-enter them. Otherwise, it'll keep the trials and the probability in there for us. And we want to go up to 4. Now I forgot the 1 minus, so we're just going to do this. Enter, and then we'll do 1 minus that. 1 minus second answer. We get 0.1375. So that's probability of exactly, or at least 5 or more. More than 10. So that does not include the 10. That's just greater than 10. So that's going to be the complement of 10. So 1, or well, the complement of more than 10 will be 1 minus less than or equal to 10. So that's going to be, well, struggling to type. I'm getting tired. Sorry about that, folks. So it's going to be a binomial CDF 1 minus again, since we're doing a greater than. So this time I'll remember to put in my 1 minus to start off. Second distribution, binomial CDF. Still 20 trials, still 0.14s are successes, but we're subtracting out up to 10 this time. We get, now I'm glad we did this one. So this gives us that scientific notation I was mentioning. This is 1.987 E negative 5. What does that mean? Well, that means 1.987 times 10 to the power of negative 5. In other words, we move the decimal point 5 spots to the left. So it's 0.00001987. What's the probability at most 8? So this is probability that X is less than or equal to 8. So this is just going to be a straightforward binomial CDF with no complement, no 1 minus. So second distribution, binomial CDF. We want 8 successes here. 0.9992. I realize I'm going really fast here just because we're pushing our time limit. If you have to, we can go back and look at the recording to slow this down if you need to take notes off of it later. Less than 5. So it's strictly less than 5. So that's going to be probably x is less than or equal to 4. So I change this to a 4 here now in our function. Second distribution, binomial CDF. Change this to a 4. .8625. Okay. What is the expected number out of the 20? That's n times p, which will be 20 times 0.14, which is 2.8. So we'd expect on average out of 20 students, about 2.8 will get an A. Standard deviation will be the square root of 20 times 0.14 times 1 minus 0.14. I'm just going to do this one off screen quick. So square root of 20 times 0.14 times 1 minus 0.14. We get 1.552 about. Next, if students are randomly selected until one is selected that has earned an A in the course, what is the probability? In other words, we're asking what is the probability that the first A is the 6th student selected? This is geometric now. Still, a P equals 0.14. So this, the 6th student, that'll be 1 minus 0.14 to the power of 5, or 6 minus 1 is technically the way it should be written, times the 0.14. Well, I'll do this first one on screen and the second one I'll do off screen. So the 6th student, so it's going to be 1 minus 0.14 in the parentheses to the power of 6 minus 1, close those parentheses and make sure we arrow out of there, times 0.14. We get 0.0659. Oops, it goes over here. For this one, the 9th student, now that's the 1 minus 0.14 or 0.86 to the power of 9 minus 1, or 8, times the 0.14. Now I wrote it out that way just because that's how I would do it. I would not type in 1 minus 0.14 in the calculator. I can do that in my head. That's 0.86. The power of 8 times 0.14. Again, I also wouldn't do the 9 minus 1. I know 9 minus 1 is 8, so it's way easier to type in 8 than it is 9 minus 1. Gives me a 0.0419. Is that probability? And what is the expected value? How many students would you expect to select before getting the first A? Well, that's 1 divided by 0.14, or 7.14. So we would expect on average the first A would be between the 7th and 8th student. That was a mouthful tonight. Sorry for all that, and hopefully that wasn't too much overload for you. Yes, there will be a formula sheet for the exam. I just posted it in week 6. Actually, in week 6, I put in both formula sheets. I put in the midterm and the final formula sheet there, so you have them to look over. So yes, if you want to go in there and look through those and print them off, you'll have those to look at and study off of. When you take the midterm exam, which is only 2 weeks away, so I'm glad you mentioned it. When you log into WebAssign, you'll have your proctor. If you're using ProctorU, they will enter it for you electronically. Or if you have a physical proctor, they'll have to type it in. They will have the password for the test. You can't take it without your proctor entering a password for you. And then once you've entered the password, it'll give you the link for the page to start the test. You'll have a button to start the test, but there'll also be a link to download the formula sheet. Make sure you download that formula sheet before you click start test. It's difficult to go back and do it if you don't do that first. So then the formula sheet will be up on your computer screen along with the test. Because it's impossible, or it's not impossible, it's difficult for ProctorU over the video camera to tell what you have in front of you. They don't allow you to bring in any printed sheets, formula sheets, just because they can't. I mean, it's hard to get them, trying to get it centered on the webcam so they can see everything on that formula sheet is tough to do. They do let you bring in scratch paper, but they'll make you hold it up and flip through it to show that it's blank before you're allowed to take the test. But so make sure you are familiar with that midterm and that formula sheet. Will you have Excel and Minitab? Yes, you will be able to use your calculator, the TI-84, and Excel and Minitab you should be allowed to have those up on your computer. Again, when you go to test, if you're using ProctorU, ask your person that is proctoring it for you if they want you to open Excel and Minitab first before you start the lockdown browser, or if they want you to wait and they lock down your browser, then you open those. Make sure you discuss that with them at the time. I'm glad you asked that as well, Richard. That's a great question. And it really depends on who is your proctor, which way they prefer to do it. But yes, you should be able to use Excel and Minitab during the test. Any other questions for the night? ProctorU is a great option. I actually think I teach some other classes where we required, this class has always been a WebAssign midterm exam and a WebAssign final since I've been teaching it. But I've taught other classes that had paper and pencil exams. And I really think we'll probably stick with the electronic exams just because they've worked out pretty well. And the ProctorU option is really great. It's very convenient for students.